Picture this. You just bought a powerful new GPU, but it wasn't made by Nvidia. You open your AI project, hit run, and it dies on the spot. No CUDA device found. Your shiny new chip is dead weight. Here is the thing almost nobody says out loud. Nvidia doesn't really own artificial intelligence because its chips are magic. It owns AI because of the software that only runs on them, a platform called CUDA. CUDA is the invisible moat. Nearly all modern AI training and inference flows through it, and it works on one company's hardware only. That is the lock-in the entire industry is quietly trapped inside. So what if you could write your GPU code once and run it on Nvidia, on AMD, on your laptop, on almost anything, with no CUDA at all? That is exactly the promise of a new language called Mojo. Mojo looks like Python. It reads like Python, but it compiles down to code that runs at the speed of C, and it can target many different chips underneath, one language, many kinds of silicon, and it arrives with a headline number that sounds fake. Mojo can run certain numeric programs up to 35,000 times faster than plain Python. Later, we will check whether that claim is actually honest. This is not a toy from nowhere. Mojo was built by Chris Lattner, the engineer behind LLVM, behind the Clang compiler, behind Apple Swift, the person who keeps building the tools the whole industry runs on. Now the obvious question from the title: do Nvidia's own chips support Mojo? Yes, you can run Mojo on an RTX card or an H100 today, with no CUDA C++ in sight. But there is a trade-off, and we are going to measure it. And that phrase, any chip, needs a reality check. Today it means GPUs and CPUs, Nvidia, AMD, Apple, the exotic AI chips, the ASICs like Google's TPU. That is the frontier, not the finish line. Then, the twist that proves this is serious. In 2026, Qualcomm agreed to buy the company behind Mojo for nearly $4 billion. So here is the full story: what Mojo is, and what it truly can and cannot do. To understand why Mojo matters, you first have to understand the wall it is trying to knock down, and that wall has a name: CUDA. It has quietly shaped more than a decade of computing, and it is the reason Nvidia became the most valuable company on Earth. CUDA launched back in 2007. It let developers use Nvidia graphics cards for general-purpose math, not just video games. It was genuinely brilliant, and critically, Nvidia shipped it years before anyone else took accelerated computing seriously. That head start compounded into a lead nobody could catch. But here is the catch: CUDA is proprietary. It belongs to Nvidia, and it runs only on Nvidia GPUs. Every deep learning breakthrough of the last 10 years was, somewhere underneath, standing on that one company's software layer. If you wrote CUDA, you married Nvidia, and on top of CUDA sits a whole tower: cuDNN, cuBLAS, TensorRT, and thousands of hand-tuned libraries. That is close to 20 years of engineering that competitors simply do not have. The chips can be copied. That mountain of software is the part that cannot. That tower is the real moat. So you get locked in. Your models, your kernels, your entire stack quietly assume Nvidia. Moving to a cheaper or a faster chip means rewriting your low-level code from scratch, so most teams never even try. They just keep paying whatever Nvidia asks. How dominant is that grip? For years, Nvidia has held somewhere around 80 to 90% of the data center AI chip market. When nearly every AI company on Earth builds on one vendor's software, that is not a healthy market. It is a single point of failure. Alternatives do exist. AMD has ROCm. Intel has one API. There is OpenCL, and there is Triton. But each one is its own island. Another dialect to learn, another rewrite to maintain. The fragmentation itself becomes the trap that keeps everyone on Nvidia. What everyone actually wants is easy to say and brutally hard to build. Write your accelerator code once, and run it anywhere on any vendor's chip. If code stopped caring which silicon it ran on, you could shop for compute on price and speed. That prize is the entire reason Mojo exists. So let us meet Mojo properly. The one-line pitch is this: the usability of Python, the raw performance of C, and the portability of a language designed from day one to target many chips at once. It is trying to end the choice between easy and fast. Mojo's North Star is to become a full superset of Python. The idea is that your existing Python code should just run, and then, wherever you need speed, you gradually add types and a couple of keywords. No rewrite of your whole world, no jumping to a second language. Just Python, with an afterburner. Take a slow Python function. In Mojo, you swap def for fn, add a few types, turn a class into a struct, and that same logic now compiles down to native machine code. Same shape on the screen, a wildly different speed underneath. You upgrade the hot parts one line at a time. Where does that speed come from? There is no interpreter, and no global lock holding you back. You get real value types, explicit memory ownership like in Rust, and direct access to SIMD, the vector units your CPU already has, but that regular Python can never reach. But the language features are not the real trick. Mojo's secret weapon is the thing it is built on, a compiler technology called MLIR. And MLIR is the actual key to this entire AnyChip story, so it is worth 30 seconds to understand. Most languages compile straight down to one target and stop. MLIR, which stands for Multi-Level Intermediate Representation, is different. It is a stack of layers that can lower the very same program down to many kinds of hardware, CPUs, GPUs, and, in principle, custom accelerators too. And here is the beautiful part. Chris Lattner created MLIR at Google while working on their AI chips. Mojo is the first real programming language built natively on top of it, which is why portability is not bolted on as an afterthought. It is baked into the foundation. Here is what that actually buys you on a GPU. Instead of writing a kernel in CUDA C++, you write it in Mojo. At build time, MLIR lowers that same source down to Nvidia's PTX, the low-level GPU code, or to AMD's format instead, with no change to a single line you wrote. And above the language sits Max, Modular's inference engine. You hand it a model, and it compiles that graph down for whatever chip you point it at, Nvidia, AMD, or Apple, all from one shared codebase. The same container ships to a cloud full of Nvidia or a cloud full of AMD, and you do not have to rewrite your world to try it. As of 2025, Mojo can be called directly from Python, so you keep your Python app and swap only the slow hotspots for Mojo. Think of it as a turbo button, bolted onto the code you already run in production. What does it feel like day to day? You install one tool, and your files end in .mojo. Modular even lets you use a little flame symbol as the extension. You write code that looks like Python, and it compiles straight to a fast native binary. No C++, no tangle of build systems. And this is a real, funded effort, not a hobby project. Modular has raised around $380 million. It open-sourced over 450,000 lines of GPU kernel code, and it is driving toward Mojo version 1. The compiler itself, though, is still closed for now. Alright, now the honest part, the reason you clicked. The title asks whether Mojo really runs on any chip instead of CUDA. So let us drop the marketing entirely and actually grade it, category by category, chip by chip. First, split the hardware world into two camps. On one side, normal, general-purpose chips, CPUs and GPUs, the flexible workhorses that can run anything. On the other, ASICs, chips hardwired for a single job, like Google's TPU or Amazon's Trainium. Mojo treats these two camps very differently. Start with normal chips because that is where Mojo is genuinely strong. CPUs are first-class citizens, both Intel-style x86 and ARM. Mojo runs on Linux and macOS, from a cheap laptop up to a fat server, with no GPU required at all. This alone already beats CUDA, which never touches your CPU. But GPUs are the headline. Nvidia is fully supported. Consumer RTX cards from the 20 series all the way up to the 50 series, and data center parts like the H100. So to answer the title as directly as possible, yes, Nvidia chips absolutely support Mojo, and they run it well. And since the middle of 2025, AMD is officially in the club too. The data center MI300X and MI325X plus consumer Radeon cards. The exact same Mojo code, the exact same container, now runs on either vendor with zero changes. That is the write once dream turning real in production. Sit with how big that is. One file, two completely different GPUs from two rival companies. Modular even showed AMD parts beating Nvidia on some large language model workloads by up to 50% more throughput in their own benchmarks. Suddenly you can pick hardware on price, not lock in. And do not forget the quiet third player, Apple Silicon, because the Max engine can also target Apple's Metal. The same model graph that runs in a data center can run on the GPU built into a MacBook. That is write once, run anywhere, stretched across genuinely different machines. So back to the sharpest question in the title. If you do run Mojo on an Nvidia card instead of CUDA, what is the trade-off? Because there is always a trade-off. You are giving something up in exchange for buying your way out of that lock-in. Let us name each cost honestly. Trade-off 1 is raw performance. Independent researchers at Oak Ridge National Lab put Mojo head-to-head with hand-written CUDA. For memory-bound kernels, Mojo was competitive, genuinely close, but on a compute-heavy case, it reached about 87% of CUDA's speed on an H100. Close, but not free. And remember that 35,000 times headline from the very start? Here is the honest read. It is real, but it is measured against pure, unoptimized Python. Line it up against tuned NumPy or C, and the gap shrinks dramatically. Mojo is genuinely fast. Just treat any single flashy benchmark with a raised eyebrow. Trade-off 2 is the ecosystem. CUDA carries 20 years of tuned libraries, mature tooling, and a Stack Overflow answer for almost every problem you will ever hit. Mojo's world is young by comparison. When you leave CUDA, you leave that entire safety net behind, and sometimes you will feel it. Trade-off 3 is subtle but real. You are swapping one dependence for another. Instead of betting your stack on Nvidia, you are now betting it on Modular's platform. And remember, the Mojo compiler itself is still closed source today. You are trusting one young company to keep its promises. Now the hard limit, the one the marketing tends to skip. Those ASICs, the TPUs, the Trainium chips, Grok, Sierras. Today, Mojo does not generate code for them. Any chip is the vision. GPUs and CPUs are the reality that is actually shipping right now. Be clear-eyed about that line. And these ASICs are not a sideshow. They are the fastest growing corner of AI hardware. Google's newest TPUs now rival Nvidia's best. Amazon's Trainium is scaling hard, and Grok and Sierras are chasing raw speed. A language that could target all of them would be enormous. Mojo simply is not there yet. Why the gap? Every ASIC needs its own low-level backend, handwritten by someone who deeply knows that silicon. MLIR is what makes that even possible in the first place, but possible is not the same as finished. And filling in that missing work is exactly what Qualcomm just paid billions of dollars for. Because think about who Qualcomm is. They build the chips inside your phone and the neural engines, the NPUs, that sit right beside them. Buying Mojo is a bet that this portable, write-once approach is the way you finally reach every kind of chip, all the way down to the device in your pocket. The Oak Ridge researchers were refreshingly blunt about the rough edges too. No fast math option yet, weaker atomic operations on AMD, and a learning curve that is still very low level. Their verdict was fair. Mojo is powerful and promising, but it is clearly not finished. So who is Mojo actually for today? Teams writing GPU kernels who are tired of paying the Nvidia tax, high performance and AI infrastructure engineers who need portability, and everyday Python developers who just need one brutal hot loop to finally run at native speed. And when should you simply stick with CUDA? If you are all in on Nvidia, you need every last % of performance, and you lean on those decades of mature libraries, then CUDA is still the safe, sharp, battle-tested tool. Mojo is the ambitious challenger, not yet the default, but the direction is unmistakable. AMD is closing the gap fast. Custom ASICs are booming across Google, Amazon, and Microsoft, and a $4 billion acquisition is a very loud bet that the CUDA monopoly will not last forever. The moat is real, but for the first time it is being drained. So there it is, Mojo, explained. A Python family language that compiles to any GPU today, dreams of every chip tomorrow, runs on Nvidia without CUDA at a real but modest cost, and is honest enough to admit that the ASIC frontier is still out ahead of it. 3 ideas to walk away with. 1. CUDA is the moat. And Mojo plus MLIR is the crowbar prying it open. 2. It genuinely runs on Nvidia and AMD today. The ASICs are still the frontier. 3. The trade-off is performance and maturity in exchange for freedom from lock-in. If this finally made the CUDA story click for you, subscribe. We break down the tech behind AI, one clear picture at a time. I have been Cloud Codes, and I will see you in the next